Thank you. Thank you, Alexei, for the invitation, and thanks to all friends for hosting me here. There is a number of people who have been known for a while. It's a great pleasure to be here, and it's a wonderful institute, so we're all very lucky. So here is the title, right? And let's just keep going. So here's the gentleman in 1927. And this is the address of the institute where I work, Bleidamsweg 17. It's one of the historical addresses in the history of quantum mechanics. And the word is that Heisenberg kind of thought of this uncertainty principle when he was there. At least this is how we prefer to think about it. So, of course, everybody knows this, right? Now, what does it actually mean? Well, one definition that Heisenberg provided himself was that if you measure delta x with an average uncertainty like that, and then you want to look at the disturbance applied to P, then the disturbance, or in his words, the discontinuous change to the P is like that. And many of us probably have seen the so-called Heisenberg microscope, where in order to see the electron, you need to scatter a photon from it. If you scatter a photon, then you provide a momentum to the electron, and this all works nicely. Robertson produced somewhat later a generalization of this uncertainty principle, which connects now the uncertainties for two non-commuting variables in a certain state. And for me, it will be important because I will also be talking today about the non-commuting variables of the spin operator. So one of the stories of today will be how do we actually take a bunch of atomic spins and make them act as a harmonic oscillator. It's a beautiful harmonic oscillator, much better than the usual oscillators in the quantum sense, and I'll explain to you why. So let's talk a little bit about the position and momentum operators for an oscillator. So for an oscillator, of course, if you measure, for example, the position of the oscillator in the lab frame, then in the rotating frame, there is an operator x responsible for cosine, operator p responsible for the sine omega t. Omega is the oscillator frequency, all textbook stories. And then those two operators, x and p, they, of course, just obey this uncertainty relation again. And for the rest of the talk, h bar will be 1. So this is just 1/4. Now, how should we visualize how the disturbance comes about when we're trying to measure one of the quadratures? So look at this thing in the rotating frame. We have x and p, and we're trying to measure this x in the laboratory frame, right? So the oscillator moves. We want to measure its position. And in this way, if we keep measuring continuously, then, of course, sometimes this is 1 and you measure x, and sometimes this is 1 and you measure p. So you measure x, you put the back action into p, but in the meantime, time goes by, and so now you're actually measuring p. And you're putting the back action in x. And you keep measuring and keep measuring. And in the end of the day, you acquire the back action of the measurement in both of those operators. And then the question that I want to ask is, quantum mechanics is correct. Nobody disputes that. But can I really measure the arbitrary small displacements on both position and momentum simultaneously? And the answer is, first, this is what I want to say, right? Second, I want to put little stars there so that as to indicate that I'm not violating quantum mechanics. And finally, the answer is yes. So Heisenberg uncertainty principle and the entire quantum mechanics does not preclude you from measuring arbitrary small disturbances on both p and x of an oscillator, and this is the story that will be told today. One more important thing that we need to recall will be the entanglement of two particles in the x and p language. So this is the story from 1935, and I will not remind you about the Einstein-Podolsky-Rosen paradox, but the setting is important. So you have one particle with x and p and the other particle with x and p, and quantum mechanics allows us to know exactly the difference of x's and the sum of p's. Why is that? Because this operator commutes with this operator, right? There is this minus sign, so x1 and p1 is cancelled by x2 and p2, and cross terms are 0. So you are allowed to know this and that simultaneously, and that was the basis for Einstein, Podolsky, and Rosen to be unhappy with quantum mechanics. But since then, we've went a long way, and by now we're happy with quantum mechanics, and the paradox is not really a paradox anymore. You just have to think of the wave function, which can have an arbitrary size. A wave function can have a size of the solar system, no problem with that. 65 years later, those two groups of people actually defined the necessary and sufficient condition for the entanglement, non-classical correlations between such two systems. So Einstein, Podolsky, and Rosen talked about the system where this is known exactly and this is known exactly. But nothing is exactly known in life. So those guys, they actually defined the quantitative condition for the entanglement. You don't need to know those two operators exactly for the entanglement. You just need to have the variance of the difference here plus the variance of the sum here less than 2. And why is it 2? 2 is because from this commutation relation, if the two systems are independent, then this variance will be 1/4, this 1/4, this 1/4, this 1/4. So for independent systems in a minimal uncertainty state, for example, in a vacuum state or in a coherent state for an oscillator, then this will be 2. If it's less than 2, then the two systems are entangled. And this type of entanglement will be crucial for me because it's this entanglement that will allow me to claim beyond the Heisenberg measurements. So let me introduce a couple of oscillators that we play with in the lab. And the first one is actually something which you normally maybe don't think about as an oscillator. It's a collection of spins. They're flying around like that. They don't disappear like this. But I will actually, most of my story will be about thermal atoms, believe it or not. But it doesn't really matter much for the main message. The reason why I like thermal atoms is because I don't have to cool them. And the reason why I can work with thermal atoms is because we hold them in containers which are coated with some magic coating, which allows the spin to keep its orientation and even its superposition state after a million of collisions. So it's like a trapped system, but at room temperature. And the trapping is provided by this coating. So optically, I can orient, of course, all my spins in one direction by the process called optical pumping. Many of you probably know that. And then I will have one macroscopic orientation of the spin, and two orthogonal projections will be my quantum variables. And then I put in magnetic field, and those quantum variables begin to precess at Zeeman frequency. So this spin with a large classical value and small quantum fluctuations encoding the state, rotating in the magnetic field, is my oscillator. The other oscillator is probably much more familiar. It's just a membrane which can oscillate like in a drum mode. There could be also oscillators where electrical charges oscillate, but we will not have time today to talk about it. And the big deal about the atomic oscillator is that even at room temperature, the noise temperature of this oscillator can be close to 0, and I will explain to you why. So for our purposes, this oscillator can be initiated in a ground state at room temperature, and it will live in this ground state for as long as many milliseconds. This is in a big contrast to any normal oscillator, which at room temperature will never be, of course, in the ground state, simply because kT is much, much larger than the normal oscillation frequencies. So with respect to this spin oscillator, what is it that I will try to tell you about? There is the macroscopic value of the spin, Jx. Since it's macroscopic, I can remove the head from the top of it. And the two orthogonal projections, this one and that one, those are my quantum variables. And in the minimal uncertainty state, those variables will be approximately of the size of the square root of Jx. So once again, if you have n spins, then if they're all oriented like that, then the quantum projection of the ensemble on any of those directions, if they are unconnected and uncoupled, will be of the order of square root of n. It's like when you flip a coin n times, the mean is 0, fluctuations are of the order of square root of n. The same as short noise for light, for instance. So everybody has her or his own standard quantum limit. So the standard quantum limit that I'm talking about is this one, where you have this equality sign. And if my spins are not spin 1/2, but for instance, like cesium atoms that I play with, they have the spin of f, then I have to put f here. That's a technical detail. And so essentially, if I have uncorrelated n spins, then the best I can tell about the direction of the spin is of the order of 1 over square root of n in the angular uncertainty. So one can create a squeeze state of such oscillator, where one of the projections will have the size which is smaller than the standard quantum limit and the other larger. And as a primer, as a wake-up, if you wish, or warm-up, if you want, I will tell you about the way to generate a squeeze state of an oscillator in the first 10 minutes. But the main topic actually will be this. I want to be able, as I told you in the beginning, to do something with the precision which is like that. And what is this something? We will talk about it during this lecture. So the generic name for it will be, excuse me, trajectories without quantum uncertainties. Okay, so a little bit more about the properties of this magnetic spin oscillator. So this is the Bloch sphere. You all went through this in either quantum mechanics or maybe quantum optics course, I suppose. So the spin oriented like that. This is the macroscopic value. For example, for atomic physics, that would correspond for all the spins to be initiated in one direction along the x-axis. For example, they are all optically pumped in the upper level with +1/2 projection. Now, since this commutator stands, and remember I removed the hat from this operator because it's large and classical, then I can divide both sides by the Jx, and what I get on the right-hand side is I. And if two elephants, or an elephant and a crocodile, have the commutation relation of an I, then they're equivalent to the canonical variables x and p, right? Therefore, if I simply normalize my Jx and Jy, I will arrive at the commutation relation, which is the harmonic oscillator commutation relation. Pictorially, that would actually mean that this quantum uncertainty, which is in real life of the order of square root of n, will be normalized by the square root of n and will become 1/2, which is the normal uncertainty of the ground state. So I'm talking about the equivalence of this picture to this picture. Obviously, the equivalence is like for those in the Middle Ages who thought that the Earth was flat. It would be much better if it were flat, right? There will be no jet lag. But for us, this is called Holstein-Primakoff approximation, which essentially means that the length of this vector is much longer than any excursions from the center that we are interested in. The number of spins that I will be playing with will be about 10 to the 8 or more. Therefore, obviously, I have a nice Holstein-Primakoff approximation, and then I can approximate this part of my planet with the flat XP state. And already, like I told you, we normalize this thing by Jx, which means that we introduce the atomic x, which is Jz divided by the square root of Jx, and simultaneously Pa as Jy divided by square root of Jx. So this quadrature and this quadrature, they are now my x and p. And what, for example, if I want to go from the ground state of this system to the first excited state? What do I do? So first of all, in the picture that I show here, this is actually a negative mass oscillator. Why is that? Because if I make a single excitation in this system by creating one collective spin flip, like that, and remember that what's very important is that I don't flip one spin, number 335. I create a state where it's a superposition of one excitation distributed over the entire ensemble. In this case, I am really creating one collective excitation, which can be described with the distribution of the spin end like that. And here, maybe you actually recognize the first excited state of an oscillator, right? Because this is how it is. So the end of the vector will kind of like to be on this little circle or ring, and this will correspond to the first excited state of this oscillator. And it is a negative mass oscillator because the excited state obviously has the energy which is lower than the ground state, right? I moved one excitation here. This energy is below that energy, so it is a negative mass oscillator. And now I put everything in the magnetic field, and things begin to oscillate around the x-axis. And this is my magnetic oscillator with a negative mass. Now, what if I want to calculate the noise temperature of this oscillator? The way to do it is to calculate the number of excitations. If it's 0 excitations, then it's ground state. If it's 1 excitation, it's the first excited state. And calculating this mean photon number will be mean excitation number, can be done through the mean value of the x and p quadratures. For vacuum, this is 1/2, this is 1/2 minus 1, it is 0, and so on. So if I haven't generated a collective excitation here, then this oscillator will be in the ground state. And by the way, it is not so easy to create this oscillator not in the ground state, because this is a superposition. So any decoherence process will actually ruin this first excited state. And so this system is much easier to keep in the ground state than in any other state. Quite some time ago, we have demonstrated that two oscillators like that can be created in the Einstein-Podolsky-Rosen entangled state. And by now you know everything to understand how this works, or at least what it means. So I have two oscillators, one oriented like this, one oriented like that. So one of them has Jx positive and one of them has Jx negative. And if I now write down this commutation relation, it's 0, which means that the sum of those two operators and the sum of those two operators can be known exactly. And if you think of it, what is this number and what is this number? This is like an angle between the two vectors in the z-plane and in the y-plane. For instance, if this is exactly 0, that means that in the zx plane, those two vectors are exactly antiparallel. And if this is exactly 0, then the same holds for the xy plane. So this condition corresponds to creating a system where two vectors are exactly antiparallel, and they are in a superposition of many exactly antiparallel states, unlike the situation where we started, because we started with each of them being within this uncertainty and this one being within this uncertainty. So if I initialize one oscillator in the ground state, then it has an uncertainty. If I create an entangled state of two of those oscillators, then they are in a superposition of exactly antiparallel states. And to demonstrate that I have done that, I just need to verify that I have this condition. And this condition is exactly the condition for x and p that I told you about a minute ago, just written in the language of spins. So this is what I just told you. Spins that are more parallel than 1 over square root of n can be claimed entangled. And we create entanglement by sending a pulse of light through, and we verify entanglement by sending the pulse of light through. So I think I will go very quickly through this part. It contains some technical details which may be interesting for some of you. But essentially, the claim here is that those atoms can move around. And if I want to create collective excitations by light, then I just need the light to interact with those atoms for the time, which is longer than the transient time. And then everything is averaging out. I also need some conditions on the size of this object, but they are quite comfortable conditions. So the object of the size of a centimeter or something like that could be quite fine. All right, so let's take a little bit more of quantum mechanics here. Here is my system, and now I've drawn here the ground state of a real atom, which is cesium atom in my case. And those are the magnetic sublevels. So I initially, as we already agreed, initialize all my atoms in one state, and I take this extreme state here. Those vertical lines correspond to classical fields, and I shine them off resonantly so that I don't have much absorption. And what happens here is that if I shine this light, there could be this photon scattered, creating an excitation. And if I do it right, then the creation of this photon will correspond to the creation of a collective excitation here. So this is the A dagger, B dagger part of this operator. And A dagger, B dagger is an operator which is called an entanglement operator in quantum mechanics, because it's a creation of this particle, and they're created simultaneously, so they lead to the entanglement. On the other hand, I can also have absorption of a photon and then creation of the atomic excitation. And that would be the term A dagger B, or its complex conjugate, Hermitian conjugate. And so I can have those two interactions, and I can tune the coefficients in front of them as I wish by changing the detuning, for example, here. If those two coefficients are the same, then you add A dagger, B dagger, A dagger, B, AB, and AB dagger. And what you get is the so-called quantum non-demolition Hamiltonian, which is the product of the canonical variables for P of light and canonical variable for P for atoms. And this Hamiltonian allows you to perform the so-called quantum non-demolition measurement. So for instance, if I apply this Hamiltonian to the time dynamics of the X operator of light, I will see that if I take the commutator of X operator of light with that, it will give me P. So by measuring the X operator of light, I can actually deduce the P operator of atoms. But the P operator of atoms commutes with the Hamiltonian. So I make a measurement on light. I learn something about the atoms, but I don't change this something. And this is called a quantum non-demolition measurement. So you measure one of the two non-commuting operators of atoms, in this case P, by sending light through, and you don't change this one. So if your measurement is strong, then in fact you project your system into the eigenstate of the P operator, which is commonly known as a squeezed state. The state squeezed in the P of atoms. And I will show you in a second how this is done in the experiment. So this is the primer of the system. We have our atoms. They are initialized like that. They are put in the magnetic field, and they are oscillating in the magnetic field like this. I send linearly polarized light through this system. And as you know, linearly polarized light going through a system with the angular momentum can experience polarization rotation, Faraday effect. Since the projection of the spin on the direction of propagation changes the sign, the polarization of light will change the direction according to the Faraday effect as well. So by looking at the polarization of light here with the polarization interferometer, you will be able to read out one component of this rotating spin. The price will be that you will impose the back action on this system, very much like in the way I told you in the very first slide. We'll go through it in a second. So if you now put the signal from here onto a locking amplifier, extract cosine omega t and sine omega t, where omega is this frequency, then you will get the information about the z projection of this spin in the rotating frame and y, but you will get it with the noise because of the back action or because due to the entanglement with light. Now, let's see how we can actually overcome this limitation. So this is the layout of the experiment where we do exactly what I just told you. We also have some optical cavity around our system to increase the interaction. So we send light through, and we make a measurement of its polarization. OK, so this is the sequence of the experiment. You first initialize all your spins in the upward direction. Then this is optional, actually. You can apply the RF pulse of magnetic field, but this is if you want to do some sensitive magnetometry. So never mind that for the time being. And then you can do two things. Either you can measure continuously with light, or you can measure stroboscopically. So if you measure continuously, you are measuring on the rotating spin, So you've seen this picture before. If you do continuous measurements, then you measure the z projection, but you apply the back action into the y. And then the spin rotates, and now you're applying the back action to the z, and to the y again, and to the z again. And the longer you measure, the more quantum back action you have. So this is no good. However, if you do it at the frequency, which is twice the frequency of oscillation, then you can only measure the cosine component, for example, of this rotating spin, without touching the sine component. So in this case, you measure now, you put the back action in the y, the spin rotates, but now you don't measure. You wait. You measure again, and again all the back action goes into the y. And so what you create is a state where the z projection is known very well. All the back action goes into y, and this is a squeezed state of an oscillator. This is the result of the measurement. We used this as an extremely sensitive magnetometer because this magnetometer is only limited in its sensitivity with quantum fluctuations of the spin, and we actually can overcome those quantum fluctuations at least in one phase of this rotation. So what you have here is the dependence of the sensitivity of the measurement on the strength of this interaction, on the strength of the probe. If you do the continuous measurement, then if you measure very weakly, you don't know much. So the sensitivity is no good. You keep measuring stronger and stronger, you reach some sensitivity, but then at some point you are dominated by the back action of the measurement in the way I've shown you here. And then you get much worse sensitivity again. If you do it stroboscopically, then as you can see, you measure stronger and stronger and stronger, and then you reach the limit. And this limit is essentially defined by the strength of your measurement, which is the minimal projection noise limit of this measurement. And in our case, it was something like 150 femtotesla in 1 second of the measurement. If you repeat this measurement twice, then because it's a quantum non-demolition measurement, when you do it once and you do it again, you should get the same result. Because if you measure one projection in a non-demolition fashion, and then you measure it again, then if it was truly non-demolition, you get the same result. Well, it's not an ideal measurement, so you don't get the same result, but at least what you get is the sensitivity, which is much below the standard quantum limit for one phase of this oscillator. So doing the stroboscopic quantum non-demolition measurement, you can achieve the reduction of the quantum noise of the oscillator, but only in one quadrature. And now the question is, can you do better than that? Can you actually achieve the sensitivity to the disturbance on the oscillator, which is better than Heisenberg in both quadratures? Yeah, let's swallow the animals. So this is the story of the quantum trajectories now with the two non-commuting operators. So that's what you call classical trajectory. This is what you call a quantum trajectory. And I want my quantum trajectory look like that. I guess this thing is recorded, so you will be able to extract the references from the recording. So I need 3 steps to achieve this delta x, delta p less than h bar over 2. Step number 1 is I want to define my trajectory with respect to a quantum reference frame. I have the right to do it. I take this origin system, this reference frame, to have an effective negative mass. And I've shown you an example of the system the magnetic oscillator, which had an effective negative mass. So this is not a complete science fiction. And finally, I need to create an entangled state of my reference frame and the system of interest. And if I achieve those 3 steps, then I can do my trick. So let's go through it. Okay, so I told you that quantum mechanics allows us to create a state where the difference between the x of 2 systems and the sum of the 2 p's can be known very well, and let me just put it to 0. This is allowed. Now, what if I want to use such a state to trace the x of my system of interest with respect to the reference frame x naught? So x minus x naught is this as a function of time. What is it? It's the initial x minus x naught plus the derivative of x minus the derivative of x naught times time. That's kinematics, right? Undisputable. So this is my initial x minus x naught. But what I have here for a normal system is p minus p naught. And x minus x naught and p minus p naught, they don't commute. Therefore, just to use the entanglement with any reference frame doesn't help. Now, if I use the reference frame with the effective negative mass, then what I get here is instead of x naught dot being p naught, it's minus p naught, because it has a negative mass. Right? Right? Well, p, right, is m times x. Well, think about it. So if I have the effective negative mass, then this minus changes into the plus, and my trajectory in the reference frame of x naught is now defined by 2 commuting variables, x minus x naught at the initial time and p plus p naught at the initial time. Since they commute, I can know them exactly. Yes, please. No, because only one of the systems has a negative mass, right? So I have a normal system and a reference system. And my reference system is peculiar, and the normal system is normal positive mass. That's why not. So then if I know that, then if nothing happens with the system, then the difference between x's and the sum of the p's is conserved. If something happens to the system, like you apply some external disturbance, you will measure this external disturbance without, in principle, any limitations that Heisenberg uncertainty principle seemingly gives you. Of course, it doesn't. So a very similar approach can be used with oscillators. It's just that now you have this cosine omega t and sine omega t, and again, you change the sign here, and then again, the trajectory of one oscillator in the reference frame of the negative oscillator can be defined in principle with arbitrary accuracy. And please note that if I have an entanglement condition, which exactly means that I know this difference and this sum, which feature here very well, then I will have the measurement of my trajectory to better than Stern quantum limit. So having this entanglement with a negative reference frame is a sufficient condition to observe the trajectory with the uncertainty better than naive Heisenberg allows us. So this is the experiment where we did this measurement with 2 magnetic oscillators, one with a positive mass, one with a negative mass. And time is kind of running by, so we will do it kind of real quick. So now I have 2 oscillators, one of them with the inverted direction of the spin with respect to the other one. So one is positive mass, the other one is negative mass. I send light through, and now what I measure is the sum of the z and the sum of the y, and because one of them has a negative mass, effectively, I have the difference of x's and the sum of p's, and those two commute, and I can measure them. And now I can apply a tiny disturbance to one of them. So this is my reference frame, and this is my oscillator of interest, and this is my disturbance. And I want to apply this disturbance with an unknown amplitude and phase, and then measure and show that I can identify the amplitude and phase simultaneously, because I can identify both projections of the spin simultaneously. So the protocol goes, you first initialize your spins in those two opposite states. Then you apply the disturbance, and then you measure. No entanglement yet. So if you do that, then what you get is what you deserve. This is the end of my spin, and now for simplicity, it points into the North Pole, and I'm looking at this system from the top. So if nothing happens to the spin, then it's created here. And then I run 2,000 experiments applying the same perturbation, the same RF field. So this is my trajectory. How well do I know this trajectory? Well, the displacement is so small then that this uncertainty is actually the standard quantum uncertainty corresponding to delta x times delta p equal to h bar over 2. Okay. And now I do my trick. I do the entanglement of my system with the reference system. So I do the same, except for I perform the entanglement measurement first, and then I apply the disturbance, and then I measure again. This is what you have already seen. And this is what you get when you apply this trick. So it's not much, but it's home. So this cloud is smaller than this cloud. It's undisputable. And what's more important is that it's smaller in both quadratures. It doesn't matter how much smaller it is. This is delta x times delta p less than h bar over 2. And again, the interpretation is that Heisenberg uncertainty principle does not preclude you from measuring arbitrary small disturbances in both x and p. It tells you many things, Heisenberg uncertainty principle and Robertson uncertainty principle, but not that. It does not limit the precision of your measurements. And in this case, we have actually demonstrated that this approach allows you to measure tiny magnetic fields, which are the origin of this trajectory, to better than we could have done it otherwise. Okay, so let's see. We take a deep breath, and then I tell you about our current experiment where we are trying to do the same thing, but now by entangling the real oscillator, the mechanical membrane, big thing, you can see it, entangling it with the magnetic atomic oscillator and trying to show the same trick with the real oscillator. We're not there yet, just to make a disclaimer, but things kind of work. Yeah, let me swallow this thing. We have no time for that. It's a beautiful slide. All right. So here's what we want to do. This is my mechanical oscillator. You will see the real thing in a second. It's a nanomembrane with a thickness of about 100 nanometers and the size of millimeter to half a millimeter. So it's an object that you can hold in your hand. You put it inside the optical resonator to have the so-called optomechanical interaction. And you shine light through this thing and through our good old friend, which is the magnetic oscillator. So this is our magnetic oscillator, and it is initialized in the negative mass configuration, so that the first excited state is below the ground state. And the goal is to shine light through and to synchronize this motion and this motion to better than the standard quantum limit for both the motional degree of freedom and the spin degree of freedom. So why is it a challenge? It's a challenge because unlike the spin oscillator, the mechanical oscillator is a real oscillator which lives in the real world and couples to the real phonons of the real environment. So if you think about it, this oscillator has the frequency of about a megahertz or two. At room temperature, it has about 10 to the 7 excitations, right? This is thermal state. Even if you go to 4 Kelvin, it will still have close to 1 million excitations. What does it mean? Well, in my kind of intuitive picture, it essentially means that the state of this oscillator is a large thermal state, much larger than the ground state, and it just jumps around this thermal state with time corresponding to the exchange with the environment of a single phonon. This time can be calculated, and it depends significantly on the quality factor of this oscillator. And the quality factor, it's like, the number of oscillations that it experiences before it dies, like 1 over E. We have the membranes with a quality factor achieving 20 million. And with this, we have about 20 microseconds before those jumps occur. Well, by solid state standards, this is infinite time. So we can do things. And imagine that we're doing things that fast. Then pictorially, you think about it in the following way. My magnetic oscillator is in the ground state. This oscillator has been frozen in one of its coherent states, which actually contribute to the thermal state mixture. I make my entangling measurement, and if you don't know, then I'm telling you that for each part of the entangled state, its reduced quantum state is thermal. So I'm actually adding a lot of noise here and a lot of noise here, but entanglement means that those two noises are correlated. So I have a superposition of something like this, something like this, something like that, of course, all at once. So in some sense, this oscillator is localized in phase space with respect to this oscillator to better than the vacuum uncertainty. Right? This little red thing is smaller than this larger purple thing. So I'm willing to state that, in fact, the noise temperature of this system with respect to this system is below 0, because I can localize it to better than the vacuum uncertainty. And if you don't like it, you can argue with me. So this is the membrane we work with. Well, this is not the membrane we work with. This is a nice picture from the internet, but we used to start with the $50 silicon nitride membranes, but we now make ourselves much better devices. And all I want to show you here, this is the last piece of mathematics, I promise, is that, in fact, if you put a mechanical oscillator in an optical cavity, you can have very similar Hamiltonians to the ones that you have seen in the atomic physics. This is what ignited me, actually, a few years ago, when I looked at this optomechanics and said, come on, we've been doing this all our life. This is a very simple system. And so the way it works is if you have resonance of the optical resonator, That's the resonance. The width is the decay, and so on. And now you come with a driving field which is blue detuned from the cavity resonance. The oscillating membrane works as a modulator, essentially like acousto-optic modulator. It puts sidebands on the light that comes in. And there will be a red sideband and a blue sideband. And the detuning from here to here and from here to here will be mechanical frequency. Obviously, in this incarnation, the red sideband will be a happy camper, and the blue one will be a poor relation. So the red one will be scattered happily into the cavity mode, and therefore it will be the creation of a photon of the energy which is below the drive energy. And so this energy should be deposited somewhere, and it is deposited into the phonon degree of freedom of this membrane. So the interaction is A dagger, B dagger. It's creation of a photon in this sideband and creation of a phonon of the interaction. If, on the other hand, you tune to the other side, then you are creating a higher energy photon. Therefore, the energy should be taken from somewhere, and it's taken from the oscillations of the membrane, and therefore the piece of the Hamiltonian is A dagger B. And we've seen those Hamiltonians before for the atoms, so it's the same type of Hamiltonians, and you can tune them by tuning the driving field around the optical resonance, and you can make them a quantum non-demolition Hamiltonian, for instance. So this is as much I want to tell you about the optomechanical interaction. The point is simply that all I told you about the atomic oscillators can be applied here because the Hamiltonian is the same. So yeah, this is when we first observed the 20 million Q of our membranes. This is the photo of this membrane. This is this membrane itself, 0.5 millimeter by 0.5 millimeter, and it's actually suspended in some very special phononic bandgap structure so that it doesn't talk to the environment that much. Yes, so experiment. Yeah, so I have to tell you that this is my favorite slide, and in all lectures that I've given so far, only in one lecture I was able actually to have enough time to go through it. And you're not an exception, so we don't have time to go through it. Beautiful, no, look at that, huh? Amazing. So much work invested. So if I go to the lunch or tea or whatever with students, then you can ask me about this. It's very pedagogical. Right, so those are the heroes in the lab. There is the mechanical system, optomechanical system in the cryostat. There are spins in the magnetically protected environment. Light is sent through, and sleepless nights spent. So far, what is the cancellation of the quantum backaction? Quantum backaction is born because light that you put in has vacuum noise at the frequency of oscillation of your membrane or of your atoms. Light has vacuum noise which is white, so it also has vacuum noise at the frequency of 1.5 megahertz. It's very difficult to observe this quantum backaction. So to begin with, you just put classical noise or classical modulation onto your light, and you mimic the quantum backaction with the classical modulation just to show that the principle works. It's difficult to tweak zero, but when you add those things, then it becomes easier. And so what I'm showing you here is that we put not too many photons per bandwidth into the sideband of the probe light. And now we are looking at the noise of the membrane. And we are looking at the frequency, which is the frequency of mechanical oscillation. And what you see here is the back action on this membrane because you are measuring it with light, which has sideband oscillations at the frequency of the mechanical oscillation. We can look in the cosine quadrature, we can look in the sine quadrature. Now we can take atoms with the spin positive mass, which is oriented like that. We also see this, and we also see that, and note that the signs are the same. And now we take the atoms with a negative mass, and note that the signs are flipped. And now we take them together, and we cancel this with that to a very large extent, and cancel this with that to a very large extent. So the area of this is probably 10 times smaller than the area of this. So at least we demonstrate the principle that if you make a joint measurement, a joint measurement on a normal oscillator, the membrane, and a negative mass oscillator, your atoms, then you can cancel the back action of this joint measurement by at least a factor of 10. So that would mean that if I now apply an external disturbance to my membrane, I don't know, you want to measure acceleration, for instance. It's not very good for gravitational waves for certain reasons, but let's assume you want to measure the gravitational wave. Then you will be able to observe this disturbance with a much better sensitivity because you don't have the effect of the back action of the measurement. And we have some light in the end of the tunnel because some simulations suggest that if we cool this system to 4 Kelvin, we should be able to be close to the quantum back action regime. And if you will, you can consider this as a detector which gives you delta x times delta p less than h bar over 2. Because I can do the following. I can take my system of interest, for instance that one, and the reference oscillator, entangle them by sending a pulse of light, and then inviting you to the lab and telling you, this is my detector. With this detector, I can measure the disturbance on this oscillator with delta x, delta p less than h bar over 2. And it will be actually totally and completely correct. You will be able to measure this disturbance with respect to this detector, which now contains all those interesting guts to better than, in principle, anything. In practice, a lot. Thank you for your attention.